Okay, we have a heavy duty today. First, we should complete what is left over yesterday, and then we are going to discuss what is a necessary condition that must be satisfied by electromagnetic field across the boundary of two different medium. Okay, and then at the end we introduce a concept of the potential functions. Okay, let's briefly review what we had yesterday. We introduced the concept of phasor, right? The concept of phasor. So then in the phasor domain, or sometimes we call the frequency domain, okay? In the frequency domain, we consider the time variation of electromagnetic field is follow a sinusoidal fashion. And then we come up a wave equation, okay? So there's a wave equation in a simple case that become ordinary second order differential equations. Then we have two solutions. One corresponds to the wave propagate in positive z direction, and another solution corresponds to wave propagate in minus z direction, right? And we also introduced, we call a wave number gamma, okay? So the gamma, we know gamma is a phasor variable, and then we put a bar to emphasize this is a phasor, but sometimes you can omit the bar, right? So that we know this is a complex number, okay? So that complex number depend on not only the permittivity, but also permeability. Permittivity, but also another term is the loss term, okay? The sigma is conductivity. The conductivity. Conductivity exists in the medium, not necessarily for conductor. Even in our air, we have a moisture, okay? We have water in the air, so we have a certain conductivity, all right? Then we have, now when we deal with time harmonic electromagnetic field, we have two solution forms. One is in phasor form, okay? This is a phasor form, okay? And another is instantaneous form. So this is instantaneous form. Okay, this is instantaneous form. These two exactly describe exactly the same thing. One is using complex number. So phasor must be complex number. Phasor must be complex number, but instantaneous must be real number. Okay, this is the real world quantity. Okay, if you have oscilloscope fast enough, you can catch up the variation, the change with time, because this omega is very high, right? And then also we have initial phase for the two waves. Okay, let's suppose they're not the same, right? Okay, we have two expressions for the same electromagnetic wave. Is that clear? Okay, so those description is independent to polarization. Okay, in this case, our polarization for electrical field is in X direction. Polarization and polarization and the phasor, two different things. Okay, polarization means how this vector tip change with time, right? In what direction? And the phasor mainly tells you the initial phase, because phasor is a complex number. Okay, the initial phase. And the initial phase, why we bother initial phase? Okay, so see, if we have axis, okay, let's say change with time, this is 0. If you have a sinusoidal wave, you change in this way, compared to if you are talking about the cosine omega t plus phi. Okay, then this is phi 0, right? This is phi 0. So that means in time equal to 0, okay, you have a certain phi 0 in advance, right? So in advance, you already passed that phase, right? Or if you have another wave, same frequency, okay, then this still maximum is our reference, okay? Then this is another time phase difference, right? Right. So we really don't care about the initial phase if you only talk about one wave. But however, if you talk about more than one wave, for example, if you talk about electrical field, you talk about magnetic field, these two waves, the phase difference will make a significant difference. Okay, so we care the relative initial phase difference if you deal with more than one waves. Okay, so this is a very important. Before we talk about, you see, the electromagnetic waves without loss. Okay, the electromagnetic field. Oh, sorry, I don't have the picture. So electromagnetic field, if this is x direction, y direction. So we have electrical field. That okay. So we have electrical field is maximum magnetic field also reach to maximum. Okay. So one electrical field in the other location is changed, then magnetic field also change. So they change in phase. Okay, they change in phase. And then later on, we will say this is not always true if we have a loss. Okay, if we have a loss. Now let's say, let's talk about this case. Right? Let's talk about this case. We have a solution. Suppose we have a solution for electrical field. Okay, we have a solution for electrical field. Okay, this solution A and B arbitrary constant, complex constant, right? So we know the electrical field. Now we like to find what is the magnetic field. Okay, so electric field and the magnetic field, we have a phasor relation. What is this? This is a Faraday's law. Okay, this is a Faraday's law. This comes from the Faraday's law. Okay, we are looking for something magnetic field how to find the magnetic field from electrical field, right? Okay, then we had a phasor form. We had a phasor form for Maxwell equations, right? For Maxwell equations. If you look at this, okay, if you look at this, that means time, this is coming from here, okay? Okay, so time varying magnetic field create the electrical field. So this is the Faraday's law, right? Then from this, we can find H field by taking a derivative of electrical field with variable z, right? With variable z. Okay, we use this expression. We take a derivative with that. The first term take derivative, we multiply the first term, you see, the partial z, partial exponential function minus gamma z, right? So this equal to minus gamma z times, all right? Okay, all right. So the same as if you have taken derivative plus gamma z, then this is a plus gamma times, okay? Then we have this relation. We take derivative, we come up hy equal to this. Hy equal to this. Don't forget gamma is a complex number, right? Then we further simplify this, okay? We further simplify this because we know the gamma. Gamma, we said, gamma is the square root of j omega mu times, all right? Then this, if we take gamma divided by j omega mu, then, okay? Then, or I can say this equal to this. Do you agree? Right? So in this case, I can cancel one square root, okay, and have another one left. So this is how we got this term, right? How we got this term. Then I define this wave, we redefine the wave impedance. Okay. Why I redefine it? Because the first term, or I can say the first term stands for the electrical field propagated in positive z direction, right? So that means Hy also has two field components. One is gamma and Ex propagated in positive z direction, okay? And minus gamma in also polarized in X direction, but the propagation direction in minus z direction, right? So this is this. All right, so the A times this is my Ex positive, right? So this is Ex negative, all right? So this follow our definition. We can say that is, we can call Ohm's law for electromagnetic field is Ex in positive direction divided by Hy also in positive direction, right? So this equal to gamma, all right? Or X direction polarized electrical field, but propagating in minus z direction divided by this is equal to minus gamma. So this follow the same rule as we had in the discussion for lossless when sigma equal to 0, right? It's the same thing. The only difference right now is this is a complex number. This is a complex number. Okay, this is a complex number. All right, so I would like to go slowly. This concept, I spend more time, and then because this is so important. Oh, by the way, we are going to have a middle term exam next Tuesday. So this part definitely is covered. Okay, this part is definitely covered. And then I'd like to spend more time. Okay, and then if you have questions, don't hesitate to post, okay, in the chat. So now let's say this is a complex number. Okay, so right now the eta, I omit this head. Okay, I omit this head because this quantity is a phasor anyway. Okay, there's no real stuff which is a complex number. Okay, so eta, we said eta is this. All right, eta is this. Eta is this, right? So because this obviously is complex number, okay, then we can write it in magnitude and phase. By the way, okay, there's some concept I like to clarify. Phasor, phase. Okay, then phasor is a complex number. Okay, phase is a part of a complex number. Does that make sense? Does that make sense? Okay, say for example, we have exponential number. And I have another exponential number. Can you tell me what is the difference? And theta is a real number. Can you tell me what is the difference? Can you tell what is the difference? So what is the difference is, this is just an ordinary real number, right? This is a real. This is complex. Okay, with phase theta. Do you see? So we call there is a phase only when we have G. Only when we have G. If you don't have G, you don't have a phase. Okay. Even if you have something here, this is not phase. Okay. Phase is somewhere here. Because when you have this, take a real part, what is equal to? This equal to cosine phi, right? So that is phase. Okay, that is phase. Right, okay. Now we have a phase term. Remember for lossy case, the wave impedance is a complex number. Now let's say we like to find instantaneous expression for magnetic field. Okay, instantaneous expression. So instantaneous expression for magnetic field by definition, that is I take a real part. First of all, I already found the phasor. This is phasor. Okay, but phasor is not exactly what we want because it's not measurable. Okay, what is measurable is instantaneous is measurable. Okay, so however, to convert phasor into the instantaneous, okay, I have to take the phasor, multiply by ej omega t, then take a real part. Is that clear? Okay, don't miss anything. Then we already find the phasor, right? It's a phasor. We already found the phasor, but if you use this expression, it's very dangerous. Why is it very dangerous? Because this is a complex number, this is a complex number. If you take, say, A, this is a phasor, okay? Then the gamma Z, right? If you take this as cosine okay. This is completely wrong. All right, okay. Be careful what we should do, okay? Okay, I don't like to leave this here. This is wrong, okay? What we should do is, first, look at this gamma, okay? Sorry, not gamma, the eta. We convert eta into, magnitude and phase, right? For A, this is a phasor, right? This is a phasor. I also write it into magnitude. This is real. If real, I just write R, okay? Theta is R. I write it into everything in real, okay? Then E gamma Z, of course, I have to write it into alpha plus J beta Z, if this is minus, okay? So I have one term, this is real, right? The second, this is not real, but however, the phase is clear because we already see J. Right? We already see J. Oh. So I already see J, right? Then you can times J omega t. Okay, you decompose the phasor term clearly. Okay, write it into all in real number, right? Same as the way for that minus that direction. Then you can take a real part now because this A divided by this real number, this is a real number, okay? And this attenuation is a real number. This is a real number, right? This is a real number. And the rest of the three terms, this has a phase, this has a phase, this has a phase. Let me write it here. Is we have J theta, okay, that is something with J, minus J beta Z, okay, also J, right? And J omega T. Oh, sorry. We have J theta, J beta Z, okay, J omega T. When I multiply these three terms, this equal to, okay, very clearly is J omega T minus beta Z plus theta. Do you agree? Okay, then we take a real part. Okay, then we take a real part of this. So that equal to real part of this equal to cosine omega T. This is instantaneous term. Okay, same as for minus that direction. Okay. Now let's discuss, okay, in lossless case, okay, perfect dielectric, okay, I will go quickly, okay. So sigma will be equal to 0, not conductivity, because conductivity creates loss, right? So this gamma is simple, right? Because when this equal to 0, this is just a pure imaginary number, right? So we know gamma equal to alpha plus J beta, right? So this will be J beta, will be beta. Alpha will be equal to 0, right? So I add this, alpha equal to 0, right? All right, so we can know the phase velocity, we know the wave number, we know the wave impedance. The wave impedance, because wave impedance is the ratio between electrical field divided by magnetic field. All right, okay. Now let's look at another case, is low loss media. All right, low loss media. Low loss means the sigma not equal to 0, but very small. But how small is small? This is the question, right? Because every time it's, it's small. It doesn't make any sense if you just say the small. If you say the small with respect to a reference, that makes sense, right? So that means in English, right, if you use smaller, if you don't have any adjective or any other reference to compare, it is not correct. It is not correct in grammar. Okay, so you have to have a reference. Then what is the reference for us to measure this dielectric is low loss? Is this a relation? That means that is a function of frequency. Okay, it's a function of frequency. When sigma divided by omega times permittivity. Permittivity is a constant. Permittivity is constant, but omega is not, right? But maybe when the frequency is very low, okay, when this is much smaller than 1, okay, when frequency is very low, okay, maybe this number is large, but when frequency is high for giving conductivity, this becomes very low loss, right? Okay, because when frequency is very high, this number is much smaller than 1. Okay, so we under this condition, we call this is a low loss medium. Okay, then what is the property for the wave in the low loss medium? Okay, let's review one of the very famous Taylor series expansion. Okay, we call binomial expansion is this. Okay, so 1x magnitude of X is much smaller than 1. Okay, so this is a very useful approximation. Okay, very useful approximation. Then we use this expression apply to, not to this. Apply, you say, this is our general expression for gamma. Okay, then I take j omega outside of this bracket. Okay, outside of bracket, then we come up. We can write in this form. In this case, n equal to 1/2, right? Then we apply this up to x cubic term. Okay. So we take first the 4 terms of this binomial expansion. Okay. Then you can also do this exercise by yourself, but I did it last night, right? Okay, we can find the imaginary part and the real part of this gamma. We can write in this. So this is alpha. This is beta. Then you may notice in this class we use pretty heavily the mathematics, but not very advanced mathematical theory. But you see all these manipulations. Okay, we use calculus a lot, and this is a very good practice to train our brain, to train our methodology to solve problems. Okay, so we have alpha, we have beta. Okay, then according to this, according to what is the phase velocity, right? Phase velocity only related to beta. Okay, that is a relation between omega and beta. Then we know, hey, this phase velocity in free space, the phase velocity is this. Okay, in free space, right? In free space. But now the phase velocity is slightly slower because of this. We have a second term. Okay, but once we know beta, we know what is the wavelength. Okay, so wavelength is also getting shorter, right? Okay, slightly. Very significant things is the wave impedance. The wave impedance is a complex number. Okay, so that means electric field and the magnetic field no longer in phase. Okay, no longer in phase because the EX over HY is this, right? So they have a phase difference. Okay, this is what we had when the electromagnetic wave in low loss medium. Okay, in low loss medium. Okay, so okay, let's see what happened in high loss medium. What happened in high loss medium? In high loss medium, this condition is opposite to the low loss. Okay, let me emphasize this with Seeker frame. Okay, so that means if we have a question give to you, we tell you the frequency, we tell you the conductivity, and let you to judge. Okay, in what case? Okay, in what case the conductivity, the media is low loss or high loss. Okay, then you should take appropriate way to deal with that, right? Okay. Now in high loss case, the lambda, the general expression, it doesn't change, right? General expression, it doesn't change. Okay. But however, you see, because if we take this, okay, then we can write it in oh, sorry. Okay, so because this term is much, much larger than 1, so I can say, I can omit this. I can omit this 1, right? Okay. All right. Okay. So I can omit this 1, then this cancel. This wave number become this. This is not a pure imaginary. Okay. J is pure imaginary. This is not. Okay. So how we deal with this is okay. Then we write J is pi over 2, right? Then J square root will be pi over 2 divided by 2, right? Or J pi over 4. Right. So J pi over 4, we can write in real part and imaginary part. So this is a complex number. So interesting things is for high loss media, then the real part and the imaginary part of the gamma equal. Okay, so that means alpha equal to beta equal to the same thing. Okay, in this case, the wave number, the phase velocity, that is always defined by omega divided by beta. So that become a very strong dependent on frequency and conductivity. Okay, and conductivity, right? And then if you have a beta, then we can define a wavelength. But this number is really doesn't make too much sense, you see, because this attenuation factor alpha is too high. This attenuation factor is too high. Okay, it's so high that people define a factor. Say if we have a conductor, okay, this conductivity is fairly high. Let's say 5 times 10 power of 7. Okay, if you have a frequency, let's say that equal to 1 gigahertz. Okay, so can you find what alpha is? So anybody can find alpha. Pi frequency is Okay, then this is 4 pi times so -7, right? Tansha, can you check the mu there? Right, and then we have mu, we have a sigma. Okay, then can you tell me what is this? So anybody can tell me what is this? Okay, then people define one thing is, let's finish this calculation first. Okay, so this is pi, 4 pi, so the 2 pi, okay? Then power of 2, okay, times 5 times power of 7, okay. Then this is all right. Okay, so what that means is the wave will attenuate. The attenuation factor alpha times z. Okay, follow this, right? So this we use this is per meter. How much attenuation per meter? Okay, this is attenuation factor is how much per meter? Then let me see something wrong. Yes, this is the per meter. Okay, then people define a distance we call skin depth. Okay, we call skin depth. So people define one z equal to a particular depth. Okay, we call skin. The skin depth. Okay, this equal to that attenuation reach to minus. Okay, that means once the signal attenuate from, let's say, from 1 to 0.36, okay, one attenuation, how much distance it travel? It travel skin depth distance, okay? Then the skin depth distance is equal to 1 over alpha, right? Okay, that equal to 1 over alpha. So in this case, 1 over alpha Anybody has a calculator? So. Okay, so that means, okay, 10 power of -5 is -3 is a millimeter, right? Then millimeter is about, okay, 1 divided by 4. So that means 2.2 micrometer, okay, 2.2 micrometer. So that means at this frequency for conductor, how much the wave can penetrate into this surface, okay, into this, let me redraw this surface, okay, I like to leave this number here, okay. So that means we have a conductor, but the electromagnetic wave can penetrate, it's so thin. This thickness is the skin depth, I call skin, okay, skin depth. So the wave attenuate that much. We call this depth, we call skin depth, okay, we call skin depth. So this skin depth for this particular example, okay, let me put here. Okay, we follow this relation, okay, we follow this relation, we follow this relation. Okay, so this skin depth that allow you, the wave can go into the metal, okay? Then if this conductivity is infinitely high, there's no electromagnetic wave can go into a good conductor, okay, can go into good. So this gave us kind of idea, you see, how electromagnetic wave interact with a good conductor. All right, so okay, so let's continue our discussion of the last section of this chapter 5, okay, and then also the last material we will cover in the middle term. So that is we call a boundary condition. So what is a boundary condition, right? So far we have discussed so-called plane wave, okay, so-called plane wave solution. That is a very special scenario. Is the electromagnetic wave propagate in infinitely large medium, the one medium, the same kind of medium. Even though we discussed the relative permittivity and the relative permeability, right? But still the same material. But we know, you see, in our real world, we never deal with such scenario unless you're sitting in the space shuttle, right? And then you live in space shuttle or from satellite, you look at down to the Earth, and then maybe that is free space. You see, we have to deal with different medium, Okay, all kind and all kind of geometry, right? Say, for example, if you look around, you see the wall, you see the floor, you see the ceiling, all different material. Trees, your human body, even the human body, inside the human body, we have different organs and with a different permittivity. I assume permeability is the same, but the permittivity is different. Okay, so that means we have one medium, and then we have another medium, right? And this is third medium, right? What is the property of electromagnetic field on the common boundary? So if this is a medium 1, medium 2, medium 3, and medium n, right? What is the property of electromagnetic field, okay, across a boundary? This is a very important question, right? If we don't know this, we cannot enforce such rule in solving electromagnetic problem. We never can get a solution, okay? Because information so far we had is only Maxwell equations, okay? Only Maxwell equations is not enough for us to solve any practical problem, right? Okay, now we need to answer this question is, what is the relationship? Okay, the field point, I'm talking about a point, okay? Not on a particular surface. It's an arbitrary surface, but let's look at one point, okay? And then on both sides, what is the relation? On both sides, okay? But this distance is approach to zero, okay? If this is a distance, right? Is approach to zero, the distance, right? On both sides, right? Then we know no matter what, okay, we have to choose from what? From Maxwell equations, because the Maxwell equations is a fact, okay? So we call choose from fact, okay? You know what is the choose? Okay, so the fact is Maxwell equations, right? The fact is the Maxwell equations. So we try to from Maxwell equations to find these answers. Okay, now let's look at a plan. This is a plan. Then you are saying, hey, Professor, you just said we look at a point, okay, and then also the boundary could be arbitrary, right? Why you look at the plan? Yes, if you take arbitrary surface, very, very small, approach to zero, small, very small. This surface, you always can treat it as a plan. Do you agree? Okay, always we can treat as a plan. So that is a plan. That means we are looking at a point, right? So this is a point. We look at the plan. And then we start from integral form of Maxwell equations. So integral form, the Faraday's law, okay, and the Am's law, okay, and the divergence theory for electrical field, the divergence theory for magnetic field, okay, for magnetic field. Then let's assume we have on the surface, we have some surface current. We have some current density, and also we may have charge density, rho, on the surface, okay, on the surface, because we are dealing with surface, okay, because we are dealing with surface. Okay, we have a surface current, surface charge density, and let's use integral form. Integral form of Faraday's law by doing what we define a contour from A to B, and this contour B to C, C is on the other side of the boundary, okay? So this is A, B, okay? And then C, D, back to A, okay? I have this contour, okay? So A, B, C, D, back to A, okay? Then this contour define a plane surface. This surface is perpendicular to the surface I'm dealing with. So this surface can be oriented in arbitrary direction. Okay, I don't care. Okay, but as long as this surface defined by ABCD is perpendicular to the surface between two medium. Okay, then this C is arbitrary line integration. So I apply this C to this ABCDA. Okay, and I assume this distance, or I put here, this distance approach to 0, or BC approach to 0. So I press it, okay, I press this frame, okay. So why I press this frame? Because this S is a surface integration over this aperture, right? Over this aperture, this is my surface S, or this area of A B, C, D, right? Okay, this small area. Then because this area approach to 0, so no matter how large this magnetic field is, the integration will be 0. Okay, so this term approach to 0. But this line integration, the contribution on this side, the integration AD will be 0, right? And the integration BC will equal to 0, right? Because the length equal to 0, right? So we only deal with the integration between AB, okay, and also CD, right? Because line integration, only these two terms still remain. Okay, only these two terms still remain. Okay, but however, we know the integration CD, this is electrical field deal with differential length. Okay, this line integration equal to minus DC, right? Because the direction is opposite. CD and DC is opposite direction, right? So therefore we have this expression, the electrical field, and as a result, you see, because this is a line integration. Okay, line integration is an electrical field multiplied by the length, right? Multiplied by the length, AB, and the length of CD. This length of CD and AB dot DL. Okay, so AB, this is your vector, dot DL equal to minus, the CD dc dot dl, right? Okay, so this integration, this line integration will be equal to 0. We substitute this relation is offset sign. Okay, this is offset sign. We know, we know the result is electric field along line AB equal to the electric field along DC. Okay, in another word, in other words is this electrical field, this is AB equal to the electrical field DC. Okay, but very, very close. That means we call such a field, we call tangential. Tangential field. Okay, tangential electrical field. Electrical field we call continuous. Okay, this is a very, very important fact. The fact is, okay, the fact is, right? Okay, so we like to, so right now you say, hey, Professor, I'm not convincing, because the plan defined by ABCD, you can define in any orientation, right? So this may be true for one particular orientation. Okay, let's write it in a more general form. Okay, because if we define this, the direction of this ABCD surface is we call AS. Okay, we call AS. And the normal direction of the surface between two media, we call AN. Okay, we call AN. Then, okay, then in this case, we can write this, okay, because AS cross AN is this is tangential component. Right? You say, doesn't matter what S direction is and the AN direction is. AS cross AN is always tangential to the surface. Okay, we use this as arbitrary tangential vector. Okay, at this point. So if you change AS, you change this point, tangential point. Okay, so I use tangential point dot product with the difference of the two fields. This field can be, if this is the boundary, this is AN, okay. This field E1, this is epsilon 1, mu 1, this is epsilon 2, mu 2, okay. So for arbitrary electrical field, once I dot with a certain unit vector, that means I take a projection on this, right? So when I dot this arbitrary vector with a unit vector, that means I take a projection of this field onto this unit vector direction. Okay, so this is what we said, right? This is what we said. If we use this vector identity, this term can be equal to this. Okay, can be equal to this. So what that means is so what that means is we can have, okay, we have this expression. What this expression tells us is, okay, we have one vector, another vector, and another vector. We have a mixed product. Be very careful which operator we should do first. We cannot conduct a dot product first, because the dot product result scalar. Scalar cannot have a vector product, right? So we must do this first, right? This result a new vector, and a vector with vector we can have a dot product. That makes sense? Okay, so what that means? I change the color. We have to conduct this vector first. Okay, what does it mean is for given surface, we have normal direction. Okay, you use normal direction to cross product. Okay, so this is my normal direction. You cross any vector, what the result is. This result, any vector, that must be tangential field. That is irrelevant to how you pick ABCD surface. Okay, then you dot with arbitrary AS, that equal to 0. That means no matter how you choose your AS direction, this is always true. This is always true. This is always true. That means the tangential electric field always continuous. Okay, equal. Okay, this is a very important boundary condition. Okay, then we can extend this to another scenario. We use epsilon. Okay, we use epsilon. Epsilon is we have a curl, the curl of H, right? So if we take surface integration, so this become, right? So this is a we call a Stokes theory, right? Okay, then on left hand side, the magnetic field also dealing with line integration. On the right hand side, also surface integration. And we already know, you see, when we press this ABCD, right? Press BC and the AD side, okay? This surface integration will be equal to 0, right? Okay, will be equal to 0. And we have another term which is deal with current. Okay, this current is a surface current. This is surface current. This surface the surface current exists in two different senses. One is, for example, if this is perfect conductor, very high conductivity, health, the current only flowing on the surface, because it cannot go inside when frequency is high, because we already justified the skin depth is in the order of micrometers, right? And then the EM wave cannot go into conductor, so does current. Okay, so the current. So the current cannot go into conductor medium or only stay on the surface. So that is one scenario. And another scenario is artificial current. It's artificial current. You remember, you say let's recall. let's recall this. Let's recall this. We said we like to launch two plane waves, one propagate in z direction, one propagate in minus z direction. Then I said we to support such a wave, we must have this current on an artificial surface, infinitely large. Okay, and this current must flow in minus x direction. Okay, in minus x direction. That support a wave. The electrical field polarized in x direction and the magnetic field polarized in y direction. Then I also said, I will explain to you why we need to have such current. Did I say that? Right. Now it's time to answer this. Okay. So this is the second scenario. We have artificial current, not physical current. Okay. This artificial current can support a certain solution. Okay. Can support certain solution. Now let's see. So now you accept the existence of this current. Okay, the existence. We didn't go through the details. We just used the conclusion we just had. Okay, exactly the same thing. The left-hand side, I just change E to H. Exactly the same thing. This side, right? This side. But on the right-hand side, because even though ABCD, this area are pressed, area is 0. But because this current exists right on the surface, even though the area is 0, the current is still there. So that equal to the current density. Okay. This current density, okay, this current density means, okay, the normal direction cross magnetic field will be in the direction of the current. Will be the direction of the current. Let's recall just now, right? This is X. This is Y. We have HY. We have EX. Okay. This is Z. The current is in minus X direction. Okay. So that means if we have a surface, if we have this surface, okay, the normal direction is in that direction. Okay. So that direction cross magnetic field in Y direction, what current point to? Point to minus X direction, right? Okay, that is why we need to have current flowing in minus X direction, right? Then you may ask, then why electrical field must be polarized in X direction? That is because of pointing vector. What the pointing vector says, electrical field cross magnetic field is in the direction of wave propagation, right? In the wave propagation. Okay, so that we reveal the mysteries, okay, of the relation between EH current, okay, EH current, surface current, right? So this is the second boundary condition related to magnetic field. Second boundary condition. This is also another fact, or every fact is the first principle. So we use we solve problem using first principle. Okay, that is second relation that relate to tangential magnetic field. Okay, we talk about boundary condition for tangential electric field, for tangential magnetic field. Now let's look at how about the normal component? How about normal component? Now, to answer this, let's draw a small box. Okay, this time is not a surface, it's a box. Okay, can you see this rectangular box? Okay, this rectangular box contains two surfaces, one top surface and another is bottom surface. Okay, top surface and the bottom surface, right? Then we use integral form of divergence theorem for electric field. What that said is, okay, that said is a volume integration of D, right? Okay, volume integration of D, right? Then equal to a total charge included, okay, included. This is what integral form. But however, you see, we use the divergence theorem is this volume integration we can express as surface integration. Okay, the surface integration. Let's deal with the surface integration. Because this box, the side walls, four side walls, when I press it, the side walls area become 0. So I only need to deal with surface integration on the two surface, top and the bottom. Okay, top and bottom. Then in this case, the surface integration, this surface integration, that equal to the normal component multiplied by this delta S, okay, by delta S. And on the right-hand side, the total charge is charge density times delta S, okay. If I remove this delta S, we have this relation, okay, this is interesting relation, is the normal component of electric field flux density vector. Normal component, why is normal component? Because AN dot D, right? So doesn't matter if this is surface, if this is AN, doesn't matter what the D direction is. When I dot, this component is AN dot D, okay? AN dot D. Then what is this component? This component is AN cross D, right? AN cross D is a tangential component, the tangential component. So that is how we decompose two vector, a vector one to tangential component, one to normal component. Okay. Then when we take dot product, that means everything is normal component. We can write it into a scalar form. Okay, into scalar form. Scalar form is more clear, right? Normal component. This is interesting result. This is interesting result. Say if I have a surface, the bottom part is conductivity goes to infinity. Okay, and the top part, the relative permittivity equal to 1. That means for air. For air, right? Then I have a charge. Or even, okay, even some part you have a minus charge. Okay, so that's possible. You can partially is positive charge, partially is negative charge over surface. Very normal, right? Then I ask you how to measure the charge density. How to measure charge density? If you can measure electrical field strength, how do you measure the charge density? Then you say, oh, I can use this relation, right? Because inside the electrical field, inside conductor, okay, inside conductor, any D will be equal to 0. It cannot exist because we already justified, right? We already justified inside conductor electrical field is 0. Okay. So if it is not 0, there's another contradiction thing is the charge, if electrical field not equal to 0, you exist a charge inside the conductor. This against the physics, okay? The charge will all go to the surface, okay? So no electrical field exists inside conductor. If no electrical field inside conductor, then this relation, if this is a so dN2 equal to 0, this will be exactly equal to charge density, right? According to this, because this equal to 0. We can use this idea to measure the charge density over a surface, right? So over a surface. But if this is dielectric, then you have to measure the electrical field on both sides, okay? All right, then you take difference to find the density, right? So when we justify the magnetic field, that is straightforward because we know for magnetic field that's constantly equal to 0, right? So constantly equal to 0, that means the left-hand side, the right-hand side is always equal to 0. We only have a left-hand side left. That means for magnetic field, the normal component continuous. Okay, the normal component continuous at every point over the surface. So over the surface. So that is the basic property of electromagnetic field. We can make a summary by the last slide. Okay, we talk about tangential field. Okay, this is tangential electrical field. This is tangential magnetic field. Okay, this is a normal component. Normal component of electrical field and the normal component of magnetic field. Okay, sometimes I use H, sometimes I use B or E or D. You can easily convert by the constitutive relationship, right? So for electrical field, the tangential electrical field continuous, no matter you have a current or not. No matter you have a current or not. Okay, that's why you see when we have a current G, okay, in opposite direction of X, okay, we have electrical field on both sides, okay. They're in the same direction, okay, they continuous, Okay, but for magnetic field, it's different, right? For magnetic field, Hy, because the pointing vector in that direction, but in the opposite direction, I use different color. Okay. For magnetic field, in the other direction, on the other side of this artificial surface, must change the sign. Why must change the sign? Because we have to satisfy this boundary condition, right? And also everything is inconsistent. A pointing vector, follow pointing vector, E cross H is in opposite Y direction. E cross H point to minus Z direction. Okay, and this, I change color, and this loop equation, right? The loop equation follow Ampere's law, right? So H integration become current, right? Or you can say the tangential component of this magnetic field, the difference, that equal to the current density. Okay, to the current density. So because of this, if I give you this current density, okay, if I give you this magnitude, you can use this to determine the magnitude of magnetic field. Okay, actually, I didn't discuss this. I can leave it to you to think. Okay, throughout discussion, I didn't tell you what A is, what B is. So did I tell you this? No. Okay, but this A and B, can be determined, right? This A and B, suppose, you see, because A and B is related to the magnitude of H, right? Okay, this magnitude of H related to what? According to boundary condition, related to the current density. Okay, so this A and B can be determined. Okay, so I don't give you the answer. I let you to think, but I reserve the right to put this as one of the questions in middle term exam. All right. Okay, we have, we leave the last class. We leave the other part to discuss after middle term. Right. Okay, we stop here, but let me stop the recording